Hey guys, just decided to put together this quick video to give you a demo of the two most important tools that we have to improve Julia's speed. And hopefully this will help you on your homework. So on the right, we have this demo.jl file. We've got an input, which is 10 million normally distributed random numbers. Then we've got this function relu. This is implemented kind of poorly, but basically what it does is if x is less than or equal to 0, it returns 0. Otherwise, it returns x. We'll learn why it's called relu in the future in this class. But this is implemented kind of poorly on purpose just to demonstrate a point. Then we have this function do stuff that takes an input. It creates this output vector, calls relu on every element, pushes it, and then sums it. And then we have the time macro to see how long this takes. So we can include this and let it compile, and it takes about 3.5 seconds. We'll run it again just to make sure that wasn't compile time. That took longer. So let's say we'll count this as 4.0 seconds to start out to do all these calculations. So whenever you're optimizing any code, you always want to profile. If you're not profiling, you're not doing real optimization really, because you can't see which parts of your code are fast or slow, so you're just guessing. So in Julia, there's a package called profile view, which makes it really easy to understand the profiles that you run, and you can use the prof view macro to do this. You just type the function call, and that will profile, which means it'll run the code and take a bunch of samples of where in the function it is at that given time, and then it'll collect that data and output it. And this one takes a few seconds or a little bit of time just because this function itself is kind of poorly written. So this is what's called a flame graph, and it gives you information about how much time each function is taking. So the x-axis is time, and the width of each of these blocks is the amount of time, the fraction of the time that's spent in that function. Each of the blocks represents a function. So this right here, demo.jl do stuff line 18, this means it's spending its time close to line 18 of the do stuff function. And then blocks above are called by blocks below. So we're not actually spending very much time in the do stuff function itself, but we're spending more time in the functions that it calls. So what you really want to look at are the things on the top, because that's where the actual time in the code is spent. And you really want to look at yellow and red blocks. So yellow blocks represent, they mean that there's an allocation happening there. Or typically that's what they mean. And then red blocks typically mean that there's a type instability, or somewhere where Julia can't infer what the concrete types are. So maybe the easiest, let's take a look at this, because this will be easier to fix. So we see in do stuff, in push, we're getting an allocation. So let's see if we can look into that. So we look here and we see that we're calling push here. But if we look at this code, we kind of did this inefficiently because we're just taking the sum at the end. So we don't really need to take a vector and push a bunch of numbers into it, because that's growing the vector and that's causing it to have to allocate more memory. So instead, what we can do is just say s equals 0. And then instead of doing this push, we just do s plus equals this temporary variable. And then we can just return s. So let's see how that does. Include that. And first time might be some compile time in that time. But yeah, it looks like we've gotten down to 1.3 seconds just with removing allocations. So that's a pretty good improvement. Let's close this old flame graph, and now we can look at the new flame graph. Let it do its profiling. Okay, here we go. So we got rid of all the yellows. There's no more allocations happening. You can also, well, that's the at time allocations is sometimes inaccurate, so don't look too closely at that. Profile view is much better. So now we see that we have these red lines, which indicates that there's it's not able to infer the types. So we've got do stuff line 20. We're having some type trouble. So this introduces the second most important tool, which is code warn type. So we can use the code underscore warn type macro on do stuff. And what code warn type does is it partially compiles the code and then infers all of the types of the variables. And then this is a printout. These roughly correspond to different lines of the code. So you can see that this like s equals s plus temp, corresponds to this line. And you can see the types that it's able to infer for all the variables. So it says s is of type any, so it wasn't able to infer anything about that. And then we look at temp and we see, oh, this could be a bool, a float 64, or an int 64. So when it adds to s, it might end up changing the type of s, which is really inefficient. So what we need to do is make this type stable. So as you can see, if x here is a float, it might return an integer 0, a bool, or a float. So we need to make sure that it always returns the same type. So we can do that just by deleting all these lines, saying if x is less than or equal to 0, return 0.0, which is now a float, else return x. So let's include that. And now we're down to 0.16 seconds. So that actually gave us almost, a factor of 8 improvement. And then we can profile that one more time. And if you don't see any red on the top level, then that means that you've gotten rid of all your type instability. So this is about as fast as it can compile this algorithm. So then you need to start looking at the algorithm and seeing if you can actually improve the structure of the code like that. Let me make sure this version. Yeah. So there you go. We've improved this by a factor of, I don't know, let's see, 0.16 divided by 4. So we've reduced the runtime to 4% of what it was with those two tools. All right, hope this is helpful, and I'll see you guys in class.